how are we doing today?
Exhausted. You?
Exhausted. Yeah, it would be good if we were all asleep, I think. That would be helpful.
Asleep. Wait, you guys got to sleep? I worked all night.
I'm just confused.
Same.
How can I help?
Why is life the way it is?
Because if it wasn't the way it is, it would be some way else, and we'd be saying, why is life like that?
Sure.
Are you sure you're not a theoretical physicist?
Yes. So, Allison, how can I help?
Oh, I was just confused on the homework. Well, probably what we'll be talking about today. So.
I can just launch into my spiel, and if it helps, great. And if it doesn't, be sure to ask stuff, okay? It's always good if I can, the stuff I'm talking about actually helps you guys. What's that?
Nothing.
Okay. Okay. So where are we so far? We've got a couple of tools that we need to kind of put together. We've got a couple of triangles that we talked about. For those standard triangles, for those standard angles. And we talked about allowing that hypotenuse to be 1 in our pi over 4 triangle, or 45-degree isosceles triangle. And we use a little Pythagorean theorem to compute in ratio what those side lengths would be. And that could, that allowed us to know what the sine, the cosine, the tangent was of pi over 4 radian angles. We also looked at the pi over 3, pi over 6 right triangle, or the 30-60 right triangle, and found that, again, if we let that hypotenuse length be 1, we could compute that this short side was 1/2, and this long side was the square root of 3 over 2. Now, as I mentioned when we talked over that, your textbook likes to have, I think for the 45 isosceles triangle, or for the pi over 4 triangle, it likes to make these side lengths 1. And it's certainly true that, you can make those side lengths 1 and then compute the hypotenuse to be the square root of 2. It's the same triangle, just with slightly different ratios. You can also let, for the 30-60 triangle, you can let this length be 2, compute this as 1, and that at the square root of 3. That's just a triangle twice the size of the one we have. And you get the same ratios. But I like to have this hypotenuse, oops, that's not what I wanted to erase. I like to have this hypotenuse of 1, not just because it allows those sine and cosine ratios to be over 1, which is nice. But for what we're going to do today, you'll see that that hypotenuse of 1 is super, super handy. So we talked about these triangles. Any questions about those triangles before we use them to do our stuff today? Okay, because those triangles are going to be our friends. We also have looked at our circle. Hopefully you guys watched the stuff I sent out on the circular definitions for our trigonometric functions. Yes, no, maybe.
Yes.
Yes. So for example, if we have an angle in standard position and say the point out here is at, oh, let's say it's at 5, 6, just for the fun of it. That means this length here is 5, that length here is 6. If we want to know, I'm going to call this angle phi. If we want to know, say, the sine of phi according to our circular definitions, instead of being opposite over hypotenuse, it's our y value, which is in the opposite position, triangularly, and the radius of that circle. So it's going to be the y over r. Now, we don't directly know the radius of that circle, but luckily a little Pythagorean theorem can tell us that. Or, frankly, is it Pythagorean theorem or is it the equation of the circle? Well, that would
Matt,
be
I have a
equation of the
question
circle.
about
Chio, yeah.
that. So when we have a triangle like that, are we always going to assume that it's a right triangle?
Well, this is the y distance and this is the x distance, right?
Mm-hmm.
And the x-axis and y-axis are by definition orthogonal, by definition perpendicular.
Okay.
So that forces this to be a right angle.
Okay.
Does that make sense?
Yeah. No matter where it is on the circle, it's always going to be a right triangle.
Yes, because our x and y are forced to be perpendicular.
Okay. Thank you.
Sure. So whether or not this is x squared plus y squared equals r squared, our equation for a circle, or a squared plus b squared equals c squared, Pythagorean theorem, they're the same formula. The equation for a circle is really just an example of Pythagorean theorem. So, we could have a cool discussion over like, no, it's a circle. No, it's Pythagorean theorem. No, it's a circle. It's the same formula. Same tool. So that 5 squared plus 6 squared is the square of our radius. So 25 plus 36 is 61. So our radius is plus or minus the square root of 61, but because it's a radius, it's always going to be considered positive. Okay, so that's the square root of 61. So our sine value for that angle would be our y over r, an allegory for our opposite over hypotenuse. So 6 over the square root of 61, which you would, of course, rationalize. Fair? You guys are quiet today. Now, again, the nice thing about this definition, one of the reasons we have this expanded definition, is we need to be able to have angles that don't live in right triangles. So that angle, whatever it happens to be, it's an angle in quadrant 2, and we can't draw a right triangle that has that purple angle as an internal angle. So I need to be able to define our functions based on something that doesn't require that right angle to exist. So let's say, for sake of argument here, let's say we knew this y value here was 4. So that point is something 4. Still on this circle of radius square root of 61. Could we compute that x value? I want you to take a moment and do that. There's a issue that's going to come up that I want to see how how you guys respond to. So take a minute, knowing that the radius here is the square root of 61, and compute that x value. Oh, Thomas, I always hate when classes are too quiet, even in-person classes. That doesn't mean I like people talking about like what's new on Instagram, but questions and feedback and, you know, talking back and forth about what our stuff means.
So I mean, we can't really find that, can we? Since
Well,
oh wait, we can. I'm sorry.
because we know the 61, yeah.
Yeah, I
Without
forgot.
that, you're right. We'd have nothing without that. But the fact that it's in that same circle.
Yeah.
So either put it up in the chat or verbally suggest what you turned that into.
I turned it into 3 square root of 5.
Okay, so you took that square root of 45, conceptualized it as the square root of 9 times 5. Square root of 9 you knew was 3 square root of 5.
Mm-hmm.
Okay, so I like the 3 square root of 5. Still just a little grumpy there, though.
I put it as a negative exponent.
Well, we certainly know that when we square root both sides here, we do get plus or minus, right? That 3 square root of 5. But you said that you specifically chose the negative. What
No,
told you to choose the negative?
I used a negative exponent. I don't know why. I just instinctively did that when I was doing the math. I have no clue why. When I was doing square root.
Yeah, that would be a fractional exponent as opposed to a.
Yeah.
Okay. But we certainly do know we get a plus or minus in there, right? But before, we've been saying, oh, okay, yeah, it's there, but we're going to throw out the negative because we're in triangles or it's a radius. But we're in quadrant 2 over here. What do we know about all the x values over here in quadrant 2?
Negative.
Be negative, yeah.
Yeah, all those x values are negative. So we need that negative value. Fair? So if we're asked for, say, sake of argument, the cosine of that purple angle, I'll call it theta, then it's going to be, again, we could try to say our adjacent over hypotenuse, but again, this purple angle, this is the angle that we're talking about. That big purple angle can't live inside an actual right triangle. You can't have because a right triangle has to have an angle at 90 degrees. And if it then had this big angle at, I'm going to say that's 130-ish degrees, something like that, you've already gone past 180. That purple angle can't live in a right triangle. So the idea of the opposite and adjacent and hypotenuse of this triangle, there is no triangle. But if we go to our other definition, our x over r definition, then our x value is just the negative 3 square root of 5 that you found. And I do like that you simplified that over that square root of 61, which you would again then rationalize. Oh God, it looks ugly when you rationalize it. What, negative 3 square root of 305, I think it is, over 61. Ugh. Questions about it, about any of that? So that's a little bit of direct application of all that information I sent out. But how you guys feeling about all that?
Feeling good.
Good. I did mention in that thing I sent out that some people kind of go, well, there is sort of a right triangle here. You're certainly not wrong. We certainly see a right triangle here. And it has an opposite length that has an adjacent length. The angle we're talking about isn't an internal angle to that triangle, but there is still sort of a triangle there. And if you think of this as the opposite side and that as the adjacent side and this as a hypotenuse, which in terms of the drawing of that triangle, they certainly are, then our adjacent over hypotenuse logic still works, as long as you're okay with saying, hey, that length is negative. As long as you're okay with the idea of negative length, which really you shouldn't have a problem with that, it just takes a while to get okay with it, your triangle logic can still hold. Excuse me. These circular definitions really aren't supposed to be different. They're just supposed to be expanded. Okay. So let's put these two ideas, out of the way. Put these two ideas together. The idea of our nice circle, I want to put that together with these triangles that we were talking about. Come on, work with me here. There we go. So we spent a little bit of time talking about constructing our standard angles. So if we went in here, we knew that was from 0 radians in standard position over to 2 pi radians. Half of that was pi radians, half of that pi over 2 radians. If we counted it, 3 pi over 2 radians. Half of the pi over 2 would be pi over 4. And I asked you guys to practice doing this to kind of get a good feel for your radian measures. Have you guys been doing that? Some of you have. So pi over 6, pi over 3. It is often the case that I get people saying that I'm struggling with radian measures, and I ask, well, how's it coming when you try to count this out? And they go, oh, well, I haven't really done that. And I go, you haven't done that and you're having trouble with radian measures? How could that possibly line up? Okay, I don't say it that sarcastically out loud, but I feel it. So you really want to get to a point pretty soon where you can just draw those out fairly quickly, so you can be thinking through them. But if we allow the radius of this circle to equal 1, this becomes our unit circle. And yeah, it becomes our unit circle. So if we consider the points of intersection at those standard angles, we know that, let's say, for example, at this pi over 6, if we knew that x and y value, I don't know why I'm using green. If we knew that x and y value, we would know that the sine of pi over 6 was the y value, and the cosine of pi over 6 was the x value. Divided by 1, because that's our hypotenuse length or radius length, but still, if we knew that x and y coordinate, we would know the sine and cosine of pi over 6. And if that's true for all of these, if we knew the x and y coordinates at the 5 pi over 3, if we knew those x and y coordinates, we'd know the sine and cosine values. But we need a way to find those coordinates. Well, we have a way to find those coordinates. These triangles. If you take this triangle at its current scale and place this triangle in our circle, it fits right there. That pi over 6 angle there is the same as that pi over 6 angle. The hypotenuse of 1 is this radius of 1. This pink triangle here fits perfectly right there, which is why I wanted that hypotenuse to be 1, by the way. So what does that mean? Well, that means the short length, our y value, is 1/2. That long length, our x value, is the square root of 3 over 2. And boom, we know the coordinates of that point. So if somebody comes along and says, hey, what is the sine of pi over 6? Well, the sine is supposed to be the y value of its intersection on the unit circle. So sine of pi over 6 is 1/2. Cosine of pi over 6, square root of 3 over 2. The x value. Tangent at pi over 6, y over x, so 1/2. Why did I put 6 there? Sorry. Square root of 3 over 2. 1/2 over the square root of 3 over 2, which would be 1 over the square root of 3, which would be the square root of 3 over 3, rationalized. And we're just going to do that same thing with all of these triangles, with all of these points, to make all of these triangles. So, for example, at pi over 4, I want these coordinates. Well, if only we could do the same thing. Well, can we grab this triangle and put it right here? Hopefully behind all those black squares with your names, you're all going, yeah, we can totally put it right there, dude. And that means we know what these lengths are. Again, because we let that hypotenuse value be 1 and our radius value is 1, that x and y coordinate are the square root of 2 over 2 and the square root of 2 over 2. I'm not going to go through all of them again, but that does mean that, okay, what's the sine of pi over 4? Well, it's the y value, square root of 2 over 2. Okay, I'm going to do all of them. Cosine of pi over 4, it's the x value. Happens to be the same because of this symmetry. Tangent of pi over 4, it's the nice one. Y over x, square root of 2 over 2 over square root of 2 over 2, 1. And we could do the cosecant, secant, and cotangent just by taking those reciprocals. Okay, what about that next one? Well, ideally, you'll notice that that pink triangle, if we rotate it, also fits there. More in this orientation, where the pi over 3 radian angle sits right there. It's the same triangle, just up on its end instead of laying down flat. Draw it in there poorly. I recommended getting yourself a couple of those drafting triangles. This is kind of wide, so you can make yourself a circle and move these triangles around and see how they all fit in there. But because it's essentially the same triangle, it's going to have the same values, except the x value is the 1/2 and the y value the square root of 3/2. So again, what's the sine of pi over 3? Well, sine of pi over 3 is going to be the y value, square root of 3/2, and so on. Now, for these other standard angles, are we going to need different triangles? We're just going to need to flip them and rotate them and play around with them, because they're still going to fit in the same locations. That pink triangle is going to fit down here. That, I'm going to go with orange triangle, is going to fit on all of these pi over 4s. You notice we are always referencing our triangles to the x-axis, not to the y-axis. That is important to keep our x's and y's appropriate. But we can go all around just flipping and rotating these triangles to get all of these coordinates. For example, over here at 5 pi over 6, okay, that y value is still that short height at 1/2. But notice the x value, okay, its raw length is still the square root of 3/2, but because we're in quadrant 2, it's going to be negative. So if somebody comes along and says, hey, what is the cosine of 5 pi over 6? Well, 5 pi over 6, it wants to act a lot like pi over 6, but because we're in quadrant 2 and we're talking about cosine, so x values, it's going to be that negative square root of 3/2. Sine at 5 pi over 6. Well, sine in quadrant 2, y values are still positive in quadrant 2, so sine is positive in quadrant 2. It's 1/2. The y value. Could you take these triangles and fill out all the rest of those coordinates all the way around? Ideally, yes, we could. This one down here, it's the pi over 4, so it's the square root of 2/2 and square root of 2/2. It's these square root of 2s/2s. But down in quadrant 3, the x and y are both negative. And we can just build this whole thing.
What about quadrant 4?
What about quadrant 4? Which one do you want to do in quadrant 4? You want to do the 5 pi over 3, the 7 pi over 4, the 11 pi over 6?
7 pi over 4?
7 pi over 4, okay. The 7 pi over 4, it's the pi over 4s, so it's going to be that orange triangle. Does look like stained glass. Because it's the pi over 4, we know the side lengths of those square roots of 2/2. So the x value is square root of 2/2. And it's going to be positive because we're in a positive x quadrant. But this length is going to be negative because we're down in quadrant 4. So that's going to be a negative square root of 2/2. really for these standard angles, there are only three numbers you're going to get, but they're going to be either positive or negative, so technically 6 numbers. On the 6s and 3s, you're going to get the 1/2 and the square root of 3/2. On the over 4s, you're going to get the square root of 2/2 on both coordinates. So really, we could just go around and determine all of these, and you'll notice, ideally, some very nice patterning. Like over here, this 4π/3. It should really be the same as these other over 3s, just the signs will be different. It'll be a negative 1/2 and a negative square root of 3/2. Up here, it'll be a negative 1/2 still, because again, we're in quadrant 2, so the x values are negative. But you'll have a positive square root of 3/2. π/4, square root of 2/2, and square root of 2/2, but the x value is negative. Yeah, we might as well fill the rest of it. We only have one more, right? It's going to have the long x value, so the square root of 3/2, negative in that quadrant. The short y value, 1/2, negative in that quadrant. Fair?
Yes, thank you.
Sure. Now, I'm going to ask some sneaky questions because that's fun. Let's say somebody wants to know the cosine of negative 5π/3. Well, negative 5π/3, I don't have a label for negative 5π/3. But I don't need one. As long as we can find something coterminal to negative 5π/3. So let's find something coterminal to negative 5π/3. I'm going to need to redo my diagram in a minute here. It's going to get a little crazy. But what's coterminal to that negative 5π/3? Well, if we start at 0 and count negatively, then that's negative 1π/3, negative 2π/3, negative 3π/3, negative 4π/3, negative 5π/3. So negative 5π/3 is coterminal to 1π/3. Coterminal to 1π/3. So if you are a negative 5π/3 angle, you are in that same position. You are coterminal to π/3, which means you intersect at the same point. So the cosine value of negative 5π/3 is equal to the cosine value at 1π/3, which we know. The cosine is the x, so 1/2. We could even get, fairly obnoxious if we wanted to. What is the, sine of 11π/4? 11π/4, that's a couple of rotations. That's more than one rotation. Okay, but it still lands somewhere in this circle. If we can find what it's coterminal to, we can know what value it is. Heck, we already know it's either plus or minus the square root of 2/2. We just got to figure out which one. So where is 11π/4? Well, again, if we start at 0, all the way around is 8π/4. So all the way around 8π/4, 9, 10, 11π/4. So 11π/4 is coterminal to 3π/4. Sine is the y value, so square root of 2/2. Now, it takes a while to get really good at doing that, really fast at doing that. And that's one of the reasons I want you guys to build this tool because it helps you see your way through it. But once we have this tool, any multiple of our standard angles in any rotation, we can have exact values for sine, cosine, tangent, cotangent, cosecant, secant, any of them, just by knowing this diagram. Now, some of you might be asking, well, what about other angles? Well, there's two ways we can get other angles. One, I'm going to teach you some tools to build other angles out of the angles we already know. So build angles by adding, subtracting, dividing these angles. And of course, our calculator also gives us nice decimal approximations when decimal approximations are okay. But if we want exact values, we have to build them based on these tools. Okay, I got another question for you here. What is the sine of pi over 2? Because technically pi over 2 is one of our standard angles.
It's
So think-
1.
1, why would it be 1?
Um,
I'm not saying you're wrong, I'm just saying. Why would-
well, it's because with the radius of 1, that's the x would be 0
Uh-huh.
and the y would be 1. And you're asking for the sine, which is y. So it would be 1.
So we don't need any fancy triangles to tell us the quadrennial angles, technical term for the ones on the axes. Nobody uses that term, but if you're curious, they call them quadrennial angles. I always call them axial angles just because they're on the axes. So we get these coordinates kind of for free because it's a circle of radius 1. So sine of pi over 2, well, it's that y value, 1. Tangent of pi. Oh, I put the parentheses there. Pi over there. Tangent is supposed to be the y over the x. So 0 over -1 and 0 over -1, 0. Tangent at 3 pi over 2. Again, it's the y over the x. The y value there is -1. The x value there is 0. What does that mean about the tangent of 3 pi over 2? It means it's undefined. So one of the things that I recommend you guys do, not only should you get used to drawing these and constructing them, because really taking the time to draw out and build these for yourself really does build a lot of kind of ownership and understanding of this tool. But also, if you go and Google unit circle, you can grab bunches of these in all kinds of different decorations. I mean, some of these are a little, bland. Oh, that's a cool diagram. We'll talk about that later. But anyway, but you can grab some nice unit circle. Your text has some unit circles in it. What happens if we say fancy? Yeah. Pretty ones. Okay, I'm gonna have to go make some fancy pretty ones just because this is bumming me out. But Yeah, I'll make some pretty ones. But anyway, giving yourself some nice unit circles that you can have as reference for the things that we do is going to be really helpful, because we're going to pull values off of those a lot. But it really is good for us to spend some time, go through, do these constructions so that you kind of learn to feel your way around and see around this tool as we're working. Questions about any of that? No. Allison, is that helpful for some of the things you were fighting with?
Absolutely. Thank you.
Oh, good. Good, good, good. Okay, some observations, some things to keep in mind with all of this. Oops, I don't know what just happened there. It gets to be pink this time. Nope, black. Okay. So some things that are good to keep in mind. We've got quadrants 1, 2, 3, and 4. We will talk in terms of our quadrants a lot. So be sure to become really happy with what quadrants what. But some consequences of these definitions, that if we are in, say, quadrant 1, our sine values are going to be positive. Our cosine values are going to be positive. Thus, our cosecant and secant values, because the reciprocal of something positive is positive. And tangent is going to be positive, because both the x's and the y's are positive. Oops. That should be positive, sorry. So in quadrant 1, all of our trig functions are positive, just like they always were for our right triangles. Essentially, in quadrant 1, we might as well be doing right triangles. So everybody's positive in quadrant 1. In quadrant 2, okay, our sine, I'm just going to go with the abbreviations, our sine is positive because our y values are positive, but our cosine becomes negative because our x values are negative. Tangent is the ratio between the y's and the x's. So a positive y and a negative x, tangent is negative in quadrant 2. Quadrant 3, the y values become negative, so sine is negative. The x values are still negative, so cosine is negative. But tangent, the y over the x's, that ratio suddenly becomes positive. So tangent is positive down there. Who's positive in quadrant 3? Sorry, we were in quadrant 3. Who's positive in quadrant 4?
Nothing is positive.
What's that? Which one?
Nothing.
Yeah, one of them is.
That's the cosine. That's positive.
Yeah, the cosine is positive because our x values become positive again. But you're right, everybody else, other than the cosine and consequently the secant, is positive. So notice every quadrant has at least one that's positive. In quadrant 1, they're all positive. Every quadrant or every trig function has 2 positive quadrants and 2 negative quadrants. Sine is positive in 1 and 2. Cosine is positive in 1 and 4. Tangent is positive in 1 and 3. This is going to become fairly important when we start talking about inverses and solving equations, because we're often going to, like, say we're solving for something, we need it to be negative. If we need it to be negative and we're dealing with tangent, Well, tangent is negative in quadrants 2 and 4. So we're going to be searching for our answers in quadrants 2 and 4. We've got to know where things happen. So often we're going to be looking for, where is this angle, where is it possibly, or where could it possibly be? If it's sine and it's positive, we know it's got to be in 1 and 2. Let's say we know that the cosine of some angle is equal to, negative 2/3. What quadrant could that be in? Well, cosine is only negative in quadrants 2 and 3. So if we wanted to know exactly what quadrant it's in, we'd have to know some way to distinguish between whether it's quadrant 2 or 3. Well, let's say the sine of that angle, we don't know what the sine is, say, but let's say we know it's positive. So the sine is greater than 0. Well, sine is greater than 0. Sine is positive in 1 and 2. So the only place where those are both possible is quadrant 2. Fair? So that means our angle lives somewhere in quadrant 2, where this x value is a negative 2, and this hypotenuse is, at least in ratio, a 3. Could we use that to figure out what this other side length is? Well, we could use Pythagorean theorem to tell us what that other side length is, right? We'd have the negative 2 squared plus that other length squared has to equal 3 squared. So we'd have 4 plus b squared equals 9. So b squared equals, 5. So b is equal to plus or minus the square root of 5. Well, how do we know whether to use the positive or the negative?
You would just look at the quadrant. In this instance, it'd be positive since the y is positive.
Yeah, because we figured out we're in quadrant 2, we know that that value has to be positive. If we were in quadrant 3, it would have to be negative. So knowing the quadrants that we're in, knowing the relationship between our positives and negatives and our quadrants is an important set of relationships to know, because it's often going to tell us, which of the plus or minuses do we need, where are we going to have to look. It's going to tell us a lot about our different behaviors. So then, and this is going to be a common question pretty soon in your homeworks and stuff, if not already. Given this information, well, we can now say what the sine of that angle actually is. We know it's the square root of 5 over 3. And frankly, we could go and ask all of them. What's the tangent of that angle? Well, we know that's our y over x. So that's the square root of 5 over negative 2. Or negative square root of 5 halves, if we want to. And again, we could keep going. What would the secant of that angle be? Well, we know the secant is supposed to be the reciprocal of cosine, so negative 3 halves. The cosecant, the reciprocal of sine, so it's going to be 3 over square root of 5, which you could rationalize. You guys are rationalizing your stuff, right? I keep saying, obviously, you guys are going to rationalize that, but why do we rationalize? The most common answer is usually because people tell us to, or math instructors told us we have to. But I do want to kind of show you why. Let's say you took 4 over the square root of 5, and you had to add, say, 6/7. To do that, you're going to have to get common denominators. Do you want to get common denominators with a square root of 5? I don't want to either. It's just annoying. A lot of the things we do with fractions are annoying if they have a radical in the denominator. So when we hand somebody an answer, if I hand you 4 square root of 5, or sorry, 4 over the square root of 5, anything or almost anything you're going to do with that fraction, you're going to have to clean it up before you use it. So frankly, giving somebody an unrationalized fraction, it's just rude. It's not wrong. It's just rude. So we don't do it. We rationalize because it's going to make almost anything they're going to do with that thing easier. It's just polite. And that's one of the reasons as we go along, when you have something like, say, 2 plus the square root of 7 over 5 minus the square root of 3, and we're going to look at that and go, man, should I rationalize that? Rationalizing that is a pain and makes a mess. I'm not going to rationalize that. I'm not helping anybody by making that messier to rationalize it. So we're not going to, we could rationalize it. You have to multiply it by its conjugate, 5 plus the square root of 3 and 5 plus the square root of 3. And we could do that. You'd get multiple, it's just, but this, it's so quick and easy and it's just polite. Just do it to not be a jerk. Fair?
So it's just like a formality thing.
Yeah. It's not ethics, it's manners, you know? So it's not wrong, it's just rude. And frankly, there are times when you don't want the rationalized version. There are times like finding a reciprocal. It's much easier to find a reciprocal if you haven't rationalized it yet. So when you're working in practice, whether you rationalize something yet or not kind of depends on what you're going to do with it and what's happening with your problem. But when we hand off a final answer to somebody, put a bow on it, make sure it's reduced and rationalized. Fair? All right. So last thing I want to leave you with, we keep talking about the tangent being y over x by our definition. But on the unit circle, our sine value is supposed to be equal to y, and our cosine value is supposed to be equal to x. So if the sine value on the unit circle is y, and the cosine value is x, we can actually restate this tangent. If the tangent is the ratio between y and x, and the sine value is equal to y and the cosine value is equal to x, then our tangent should actually be equal to our sine value divided by our cosine value. And this forms one of our, cosine of theta. Cosine of theta. This forms one of our first identities. It's called the quotient identity because of the division, but the quotient identity for tangent. Correspondingly, that means the cotangent, since the cotangent is just the reciprocal of tangent, is the cosine divided by the sine. So this is one of the cool consequences of our circular definition, is we start building some relationships between the trig functions themselves. And we're going to build more and more of those. Ooh, since I'm going to send you off in a minute anyway. Also, the equation for the circle we said was x squared plus y squared equals the radius squared. And if we let the radius be 1 for our unit circle, x squared plus y squared equals 1. That's the equation of our circle. So that's all points on the circle. Well, for points on the circle, the x value is supposed to be equal to the cosine of our angle. And the y value is supposed to be equal to the sine of our angle. So that builds actually what's going to be a very powerful tool as we go along. It's called the Pythagorean identity. The square of the cosine plus the square of the sine has to be equal to 1, always. By the way, there is a shorthand notation for this. The cosine squared of theta. You write the square down on the cosine function itself to say, okay, when we're done finding the cosine, square our result. Similarly, sine squared theta equals 1. So we'll often see it written, we'll usually see it written this way with those squares. It's to distinguish it from being like if somebody just wrote sine of theta squared like that, it's like, wait a minute, am I supposed to take the sine of theta and then square it? Or am I supposed to take the sine of theta squared? According to order of operations, that square would happen first inside that function. So to avoid ambiguity there, putting the square on the function itself says square that result. So that's why those the kind of weird notation. So these circular definitions, not only do they allow us to deal with larger angles, they start to build a lot of relationships between, between x's and y's and sines and cosines, and starts allowing our algebra and our trigonometry to talk to each other. And that's going to be really valuable as we go along. Okay, questions about any of that before I let you go today? All right, keep sending me stuff if there's stuff that you guys need. Let me know anything else or additional stuff that would be helpful for you guys. And have a wonderful day.
Thank you.
You're very welcome.
Thank you. Thank you. Bye.
Bye-bye.